Very good evening to all the attendees and to Professor Richard, who has joined us today from Cavendish Laboratory, Cambridge, in this special public lecture, which is going to be delivered by him on the topic organic electronics. And this special public lecture is being organized under the aegis of the DBT Star College program and is part of the National Academy of Sciences India Delhi chapter and the MHRD-Institution Innovation Council, the Upadhyaya College. And this is a series of special public lectures which are being organized. And this is one of the lectures which is part of it. As a customary, I'll introduce Professor Richard to all the attendees. Professor Richard holds the Cavendish Professorship of Physics at the University of Cambridge. He is director of the Winton Programme for the Physics of Sustainability and of the Maxwell Centre. He has always taken a keen interest in the commercialization of his research and has been involved with numerous business designing and manufacturing polymer semiconductors with applications such as light-emitting diode, solar cell, and thin film transistor circuit. He is the recipient of several awards for science and engineering, and in 2003 received a knighthood for his services to physics. His research encompasses the physics, material science, and engineering of semiconductor devices made with carbon-based semiconductors, particularly polymers. His research group was first to demonstrate using polymers efficient operation of field effect transistors and the light-emitting diodes. These advances revealed that the semiconductor properties of this broad class of materials are unexpectedly clean so that semiconductor devices can both reveal their novel semiconductor physics, including their operation in efficient photovoltaic diodes, optically pumped lasing, directly printed polymer transistor circuits, and light-emitting transistors. With these words, I request Professor Richard to kindly share his screen.
Well, good evening, and it's a real pleasure for me to have this opportunity to provide you with the view we have been building up in Cambridge about what we can do using molecules to do electronics. I'm going to start somewhere where you probably don't expect me to start, and that is I want to contemplate for a bit how we view the different materials worlds that we do electronics or chemistry with. I would perhaps call this our sort of materials multiverses. And I was intrigued reading a book on cosmology and quantum mechanics by Max Tegmark. He's a cosmologist in Boston called Our Mathematical Universe. And one of the contemplations that the cosmologists have is that besides our universe, there may be parallel universes. And indeed, some of the laws of quantum mechanics make it hard to exclude that. But those other universes may have strange properties. There's a sort of hierarchy of different parallel universes. And a level 2 multiverse, which is one that is quite much discussed, is one where there are parallel universes where the laws of physics are the same in all of them, but the fundamental constants are not. So the mass of an electron might be different, or the permittivity of free space might be different in different parallel universes. But actually, that's what we do in the electronic materials world. We've been doing it for half a century. So let me start and explain a little bit more what's on the screen at the moment. And here we have a vacuum. And I'm going to put two charges together, one a positive charge on a proton and the other an electron. And of course, you know that that makes a hydrogen atom. And you will know from the dawn of quantum theory that that produces a bound state, that the electron sits in orbitals. The lowest orbital, the 1s orbital, sits 13.6 electron volts below the vacuum level when the electron and hole would be free to separate. And indeed, the electron is very tightly bound to half an angstrom to the proton. And that's just putting in the standard electrostatic interaction into Schrödinger's equation. And of course, that produces energies, binding energies, which are much, much larger than thermal energy at room temperature, KT. And what we're talking about here is chemistry. I just briefly mentioned that if I go from a hydrogen atom to a helium atom, where I've now got 2 electrons, the first excited state, I have an electron in the 1s level, and the second electron has been promoted to the 2s level, and it could form a spin triplet state, which is lower in energy than the singlet by, again, quite a large energy, 1 electron volt. So why am I telling you about this? Because you know this from your first courses in quantum mechanics. Well, when we go to a semiconductor, like silicon or gallium arsenide, we move to another parallel universe where we have increased the epsilon, the permittivity, by typically a factor of 10, because the semiconductors screen, the core electrons screen electrostatic interactions between, say, a plus and a minus charge. And one of the consequences, you can see I've got a sort of regular square polka dot pattern, which sort of represents where the ion cores might be in, say, silicon. That regular crystalline lattice has the effect of renormalizing the mass of particles, and typically the mass is quite strongly reduced, typically to say 1/10 of the electron mass. So if we now put together a plus charge, which is now a hole, and the minus charge, which is still an electron, they still interact through the Coulomb interaction, but it's now screened because we have the dielectric medium, and the masses of the particles are small. And what that does is to change the energies from electron volts to, by a factor of 1,000, to reduce them to milli-electron volts. So the binding energy, the Coulomb attraction that keeps electron and hole together, is perhaps 10 milli-electron volts for the 1s hydrogenic state. So we've reduced the bonding by a huge factor by selecting different mass and different dielectric constant. It's a different universe where electrons and holes are not thermally bound, and we think of silicon producing good solar cells where light is absorbed and it produces free electrons and holes. And of course that's very well developed, and that's the world that we know makes semiconductors work. Now, so there in grey is the vacuum, in blue is an inorganic semiconductor, and molecules sit somewhere in the middle. I will show you some examples. But if you go to a carbon-based molecule, the dielectric constant is not very high. There are just not enough other electrons to screen the Coulomb interactions. And a typical value for the dielectric constant will be 3. Anything organic has a refractive index of less than 2. So that would give a maximum value of epsilon of, say, 4. And the mass is not much reduced. So the effect is that the electron and hole, which are free to separate in silicon, are now quite strongly bound by perhaps half an electron volt. It's much smaller than the hydrogen atom, but it's still a strong binding. So that means that when I go to a molecule, which might have semiconductor properties, I would expect that when I absorb a photon, I will produce a molecular excited state. I won't instantly get free electrons and holes. And it's living in that world where the Coulomb interaction is large, but nevertheless just about allows semiconductor behavior that is the big puzzle that we've been teasing out to produce some useful technologies. So let me turn to some real materials, and this is not a chemistry lecture, so I'll keep the chemistry to a minimum. But here is a polymer chain. The six-membered ring is a benzene ring or a phenylene. There are 6 carbons, and then I've got hydrogens on these 4 carbons, and then I link in 2 directions, to the left and to the right, to another carbon. In this case, I've got a carbon-hydrogen, carbon-hydrogen, and then on to the next phenylene 6-membered benzene ring. And that's my repeat motif that makes a polymer. Now that material, which is a material which was very important to us because we were able to make a light-emitting diode with it 30 years ago, is fluorescent yellow-green. It's very brightly coloured, and it's brightly coloured for the same reason that graphene is black. So I'm going to turn for a moment to graphene because that provides perhaps the most familiar these days example of what the electronic structure is. So what you see on the right-hand panel is that I have put the motif for the repeat unit of this polymer onto a honeycomb network, which is the graphene sheet, and you see they sit perfectly on top of one another. And that reminds us that the chemical bonding we've got puts one carbon forming just 3 bonds at 120 degrees to one another to the 3 nearest carbons that lie in the sheet. It's 2-dimensional bonding. What's left over is a non-bonding PZ orbital on the carbon, which will weakly overlap from one, the orbital on one will overlap to the orbital on an adjacent carbon and form a weak, rather delocalized chemical bond. These are the pi bonds, and the electrons contained that are stored in them are the pi electrons. In the case of graphene, there is no energy gap between the filled pi states and the empty pi star states, so it's black. But by the time we go down to a polymer or a molecule, we've pushed an energy gap. So this is a perfect nanographene ribbon. We've now got an energy gap between electrons and holes, which gives and it's well into the visible spectrum, and we have this nice visible band gap yellow-green material. Now, that story needs a little bit of thinking about, because what I've pointed out is that electrons and holes, if they were present somewhere on the polymer chain, would feel the Coulomb attraction, the electric attraction between one another, and would ordinarily just form a bound electron-hole pair state, which we call an exciton, and it's that gives the very strong luminescence. And actually, you can ask, well, how large a length scale do excited states visit? And a simple thing to do, because the chemistry allows it, is to look at, say, model small molecules. And in this case, it's a distyryl benzene. And actually, it's a blue emitter, but in many ways, many of the optical properties are quite similar. So this polymer, which, by the way, we can push charge in and out of, it seems to be both a semiconductor, but also just a sort of molecule that supports excited states. It's sitting rather uncomfortably between being a regular semiconductor and something where it's hard to move electrons around. But it was important for us because we managed to make an LED with it. But I'm actually going to show you a little image, some cartoons first, a little video, of a light-emitting transistor we made with one of our polymers. The polymer, if you like, the chemistry, is the thing on the bottom here. We give it the acronym F8BT. It again is yellow-green, so a band gap at about 2.5 electron volts. And what we've done is to make a transistor. So a transistor has a bottom layer, which is a substrate. That's the sort of shaded white-blue layer. We then put down two electrodes shown in yellow. The one to the left I've called the drain source, and the one to the right I've called the drain. We then deposit by solution processing or vacuum subliming the green layer of semiconductor, and in this case it's our green emitting FAET. We then put down an insulator layer, and here it's a polymer insulator, polymethyl methacrylate. And finally, we put a very thin vacuum deposited layer of gold on top, which we call the gate. And we're going to look with the camera at this device. Now, if I turn to the right-hand panel, what you can see are some black lines alternately connected to the left and to the right. Those are the source and drain strips. The length scale is that's 20 microns spacing between the two electrodes, the source and the drain. Okay, so how does it work? Well, what we usually do with a transistor, and let me start by strapping together the source and the drain, so they're at the same potential, we put a voltage between them and the gate. So if I put a negative gate voltage on, I will induce, and the dielectric is going to look like the dielectric in a parallel plate capacitor, and I'll induce negative charge on the gate, and the positive charge will now have appeared in the semiconductor, where previously there was no charge, and you can see the plus signs there. And that will be a charge accumulation, a hole accumulation layer. And if I put a voltage between the source and the drain, those positive charges will move from source to drain, and I'll get a current flowing. Now, in principle, I could have swapped the gate voltage and made it positive, in which case I would have induced electrons in the accumulation layer. It would be an N-type device. And usually, with most semiconductor devices, you have to choose either electrons or holes, because a lot has to do with the injection properties of the electrodes. But rather magically, for this particular polymer, we can get both P-type and N-type behavior in the same device. And it becomes really interesting if I now put quite a large voltage between source and drain, so I've got a minus V voltage there, and I put the gate somewhere between source and drain. I've shown it here at minus V upon 2. And if you do that, then the sign of the electric field in the dielectric is induces electrons on one side and holes on the other. And we have a big electric field because we've got a voltage between source and drain. So the electrons will be swept one way and the holes will be swept the other. And where they meet, we can get light. So I'm going to now play the video. And what you're going to see is I'm going to change the gate voltage, and it's going to sweep where electrons meet holes, emerging from, say, the source electrode and running across the channel, and then eventually disappearing under the drain electrode. So I'm going to run the little video. And what you'll see is little spots of light appearing as we start to get that line of emission. And it's now about to run across the channel. You can see some fringe electric fields as it goes, and you can see the line of of recombination sweeping across the channel. There it is. Unfortunately, it sort of dies rather than does something dramatic when in this video, because we've just taken the line of light right the way across, and then it disappears under the right-hand electrode. So there you can see lots of things all in one. You can see that we can get a field effect. The semiconductors that we're using are quite clean, so we don't have lots of defects and traps. We can get charges to travel significant distances, 20 microns. So we have semiconductor behavior. Electrons and holes can move from one molecule or one polymer chain to the next, and they emit light. Now that particular video is pretty to see, but not necessarily useful. The straight diode structures, of course, now make some pretty significant technologies for upmarket smartphones or upmarket TVs. This is the OLED. And what's remarkable is that it's been a big effort. Many people who thought they understood things said that organics would never be stable enough to work long-term as semiconductors. But they do now work, and not only do they work, but they're really efficient. And again, there were some very fundamental reasons why many people thought that they would never be efficient. And I want to talk to you about that next, because what we're looking at with those images of the smartphone and a TV are devices that work pretty close to 100% efficiency. So what's the problem? Well, I want to go back to some of the science for a moment and contemplate a little bit more what these excited states look like, what an electron and a hole look like. And I'm going to think about it. I've taken a model semiconducting molecule. It's not a polymer chain here. It's 5 benzene rings stuck together, and it's that molecule is called pentacene. It's a dark red color. It absorbs across much of the visible spectrum. The isolated molecule, the excited state, has to sort of sit on one molecule. So this is indications, I think, of the electron wave function distributed with the hole at the center. But if I put it into a solid crystal, and this is the crystal structure, you can see lots and lots of, well, some nearby pentacene molecules. Actually, the excited state delocalizes a little bit. So you've got the hole notionally localized at the center of one molecule, and the electron is then spread over a few others. But it's quite strongly bound. The electron is not free to separate from the hole. But there's a twist, and the twist is that the spin makes a big difference, the electron spin. So the example I showed you on the previous slide, where the excited state spills out over a number of molecules, is where the spin of the electron that was promoted from a conduction band, from a valence band level up to the conduction band, remained the same. So we keep an overall spin singlet state. But of course, you could, for the excited state, flip the spin of the excited state, so I can have the 2 spins parallel, and there are 3 ways of arranging that, 3 MZ sublevels, and that's the spin triplet. But the spin triplet changes the spatial wave function, and it localizes it. So the triplet actually continues, even in the crystal, to sit on just one molecule, and it's much lower in energy. It's about, and I'll come on to how much lower it is, and it's lower by the exchange energy. It's about 0.8 electron volts. It's a very large number. They're very different excitations just through the spin. And that spin dependence is due to the fact that the wave function, the electron hole wave functions are localized. So why does that matter? Well, let's have a look at the efficiency for organic LEDs. And the problem is that I can excite from the ground state where I have no spin. If I photo-excite, absorb a photon, the singlet exciton that I was just showing you is fine. That will re-emit a photon. But if I were to form the lower energy spin triplet state, it's not allowed to emit a photon because that's spin forbidden, and it's lower in energy by the exchange energy. So what do we do? I mean, now that's, you wouldn't really see that if you photo-excite, but when you bring electrons and holes together from opposite electrodes, statistically, only 1 in 4, 25% capture events produces a singlet. The 3 out of 4 produce triplets. So that would give a poor efficiency. So there's been a huge amount of work to find ways of not wasting 3/4 of the excited states. And the one that has been used in today's red and green subpixels in displays is to arrange that the triplet itself can phosphoresce. And that's done by tipping in a molecule that has got, here it's iridium, it's a high atomic number element, which gives enough spin-orbit coupling that the triplet exciton can emit itself. That gives redshifted emission, but that's been done very efficiently. But there are other approaches, the blue pixels, and what they do is to use a process which we term triplet-triplet fusion. So the story is that we bring an electron and a hole together. They bind to form a molecular excited state. If that state is a singlet, it'll give fast luminescence, fluorescence. On the other hand, if it's a triplet, it can't decay quickly because it's just a simple hydrocarbon system we're considering. And if the materials are designed well, the dominant decay channel is that two triplets fuse together in an overall spin zero state to form a singlet. So we need two triplets to make one singlet, but then we can get the same singlet emission out. And we know that's happening because it comes out at a longer time. The electroluminescence is time delayed. And that's something which can be very efficient. So I'm showing you here, the easiest way to look for it is actually to put a drive pulse through a device and then turn the drive pulse off. The time scale here is 110 microseconds, it's a log scale. And there's a fast drop off in emission as you come straight away. And then there's a delayed emission, and that straight line here is the lifetime for two triplets to make the right collision and fuse to make one singlet. It's a very strange sort of process. It appears to be, if you think of excitons as sort of quasi-particles, we don't have particle conservation. We can turn two spin one triplets into one spin zero singlet. And that is very efficient. The efficiency of that reaction can be up to 70%. That's what we've measured. And that is actually what's used to get the blue pixel in current OLED displays for smartphones and for TVs. I don't think that's the last word because we would like more efficiency and we'd like to get rid of expensive metals. Something we've been looking at recently, it's actually a collaboration, I should mention Feng Li in Jilin University in China, who was a visitor with us, who brought with him some spin radical semiconductors. So here is a little bit of chemistry. I will skip past it relatively briefly, but here we have a single carbon with bonds onto three neighboring benzene rings, they're chlorinated benzene rings. And if we break off, it's originally formed with a hydrogen, which one can remove, what we're left with is the PZ electron has got nowhere to go. It's confined at that point. It's a non-bonding electron. It's a so-called singly occupied molecular orbital, and it sits in the middle of the gap between the pi and the pi star, the valence and conduction bands. And it turns out that with the right material design, they're very fluorescent. The excited state that we get, we start off with a ground state with two electrons in the highest occupied molecular orbital. We can photoexcite and push an electron up into this singly occupied molecular orbital, in which case it's become doubly occupied. It'll drop down again. We've got very high luminescence yield in those materials. And we managed to make very efficient light-emitting diodes. There are some details about external light extraction. And what we think we can do is by working entirely in the doublet channel, the spin-a-half channel, we start with spin-a-half, we go up to spin-a-half, we go down to spin-a-half, we can avoid the problem of singlets and triplets. There's some rather curious features that we can first inject an electron onto the top half of the molecule, which goes from the ground state to now a negatively charged spin zero state. And then with the right device design, we can extract an electron off the lower part of the molecule, which is the electron donor with the carbazole group here, to produce this arrangement, and an electron dropping from the higher level to the lower level is then what gives us light emission. So we're looking to see if we can use these radical semiconductors as a way to engineer different sorts of devices. And by the way, they should do some interesting spintronic things. That's a quick run through on light emitting diodes and how they found their way into significant technology with displays. We're pretty pleased that's happened. But we could ask whether that's the most important thing that we should do to save the planet. I'm not sure what the age spectrum is of those of you who are listening to my lecture, but most of us remember that televisions used to be big, fat, heavy things with cathode ray tubes. And one way or another, modern electronics has managed to make televisions very thin. Now, whether that has made society happier is an interesting question. But what it has done is to give us some engineered materials which have been brought up to a level of engineering quality that meets the specification for displays. And we can think about using them in different ways. And a lot of our community are now thinking about solar cells. Now, solar cells, as I'm sure you all know, have become much more affordable than anyone expected. Silicon solar panels in many parts of the world now produce electricity more cheaply than any form of fossil fuel generation from gas or from oil or from coal. It's a bit tougher if you live too close to the North Pole, as we do in England, but in India there are wonderful opportunities, but even in the UK it's still attractive to do it. So silicon does pretty well. It's not that efficient. I'll talk about that later. Another measure of efficiency is payback time. How much energy or embedded CO2 have we got when we've made and installed some solar panels? Well, the measure of that is the payback time. How long you have to capture all the electricity from the solar panels before you've generated as much energy as you needed to make the solar cells in the first place. And it's come down. It's maybe a year. It used to be much worse. A year is pretty good. But let me turn on to the right-hand panel, which is some maize or corn, which I've selected that because it's one of the fastest growing plants, and it has the highest, or one of the highest, photosynthetic energy conversion efficiencies. It can run at 2 or 3%. Now, the energy payback time for a plant is not measured in years, it must be measured in days. When the plant expends energy to grow a new green leaf, it's really got to get the energy back in a very short time. Otherwise, it wouldn't grow. And the reason it's able to do that within days is because the efficiency of the construction, the amount of material used, the way it's been used, is much more developed than we have with silicon. So that sort of sense that nature is doing a more, if you like, cradle to grave efficient job at harnessing sunlight is a great guide to what's really going on. So I'll talk briefly about photosynthetic systems. To a physicist such as myself, I see photosynthesis as the most sophisticated electronic device I know of. It has a number of components. This is a sort of high-level view. There are a significant number of chromophores that absorb light. They're the antennae molecules. so that they will absorb instant light, form the molecular excited states, the excitons that I've been describing, and they're carefully designed that they will funnel energy from these antennae down into the reaction center, which is labeled RC. At the reaction center, it's like a solar cell. We split electrons and holes. And the electron goes off to do reductive chemistry and reduce carbon dioxide to produce sugars. And the hole is a sort of waste, and it ends up oxidizing water to produce oxygen, which of course is fairly helpful for us. But what makes it an interesting question, certainly to a physicist in photosynthesis, is how do green plants manage to deal with length scales? You have to move energy and you have to move electronic charges much larger distances than just within one molecule in order for the processes to work. The energy harvesting is adapted so that excitons or photons converted to excitons arrive at the reaction center at an optimum rate, because reaction centers are quite expensive to make. And that typically requires energy transfers of, say, 10 nanometers, which is sort of 20 molecules away. And again, for the electron-hole separation from the reaction center, the RC, you need quite long-range electron-hole separation. And how those work is, I mean, it was much researched in that community, which is not me, but it's a very similar question that we have to ask if we want to make a solar cell with organics. I'm going to briefly talk about energy transfer and ask how far can an exciton travel. And I'm going to briefly mention some work that we did. It's a collaborative piece of work we were doing with the group of Ian Manners, then at the University of Bristol in the UK. And what he manages, what his group can do is to make the most extraordinarily well-defined sort of nanofibers. This blue rectangle represents, if you like, the fiber. And in the rectangular core, we have a very crystalline organization of a little bit of this polymer. It's two benzene rings linked together with a bridging carbon. It's called a fluorine unit. And under the right conditions, it's extremely rigid and crystalline. And it assembles in solution because attached to it is a water-soluble polyethylene glycol chain, which is quite long. So you end up with these fibers solubilized with the sort of hairy corona side chains. And the clever thing they did was to arrange that by growing this nanofiber sequentially, they could stick something different at the two ends. And the thing that was different is a different semiconducting polymer. It's actually a polythiophene, which is colored orange here. And essentially the core, this polyfluorine, is a blue emitter, and the bits at the end are orange emitters. And what we can do is to track, when we photoexcite, what color the emission comes out. And at quite large length scales, and these are some beautiful confocal microscopy images from Bristol, you can see these fibers. They can be up to 5 microns large, and you can see they're blue in the middle and orange at the ends. But if we look carefully, and this is a small snapshot of the data, we can track how quickly and how far energy can travel from blue to orange, which it wants to do. And it's not within the optical resolution here, but it's a long distance. It's about, we've measured up to 340 nanometers, which is much, much further than nature needs to transport excitons in photosynthetic systems. And rather importantly, 0.3 of a micron is 3 times as much material as you need to absorb most of instant light. So we've got an object where we can transfer energy far enough that we might be able to if we could wire up this device so we could absorb light here, then the energy would all end up at that end or that end, and we might then transfer it to something that would say be part of a solar cell. So that's the length for energy transport. Let me talk about charge transport and solar cells. Well, there's a huge set of different approaches where the common architecture is that we want to make a mixture of two components, I mean here white and red, to form a sort of nano-structured bicontinuous film where we have two different semiconductors, one that accepts electrons, which is labeled the red one, and one which donates electrons, which would here be the white one. And the reason for having this blend is this mixture is that no matter where light's absorbed, the exciton is close enough to the heterojunction between the donor and acceptor, and at the heterojunction we get charge separation. And that heterojunction is functioning in much the same way as the special pair does in photosynthesis in the reaction center. So the key is that if we can make this nanostructure, and there are some very simple ways of making them, much less sophisticated than photosynthesis, then we can actually get light to be absorbed close enough to some heterojunction. We get electrons running upwards, we get holes running downwards, and we can make a solar cell. So the ones that emerged back in the late 1990s, we tended to mix, usually the light absorbing material was a polymer. I mean, it doesn't show very well here, but here it's a polythiophene that absorbs across the visible spectrum. And the acceptor we used was a fullerene, a C60, which turns out to have quite a low-lying conduction band minimum, so that when we photoexcite, absorb a photon in this case the polythiophene, the electron on the polythiophene would prefer to drop over to the lower energy empty state on the fullerene, leaving the hole behind, and that is the first step in the charge separation. Now, to everyone's surprise, no longer using fullerenes as the acceptors, these solar cells can now be up to 18% power conversion efficiency. It's quite a high number. It's high enough to be taken quite seriously. But it's very surprising they work. This is to remind me to say that, well, why do we need to do it? And there are many schemes to be able to directly print solar cells, because of course the organics can be printed, and there's far less material, as you can see on that printer, than there is in a silicon solar panel, where the silicon had to be sawn into a thin sheet from a silicon ingot. I'm going to divert for a few minutes onto perhaps a preoccupation of what is a preoccupation of mine, and that is one of the big surprises is that we can both make light-emitting diodes where we want injected electrons and holes to find one another, and indeed we depend on there being a strong Coulomb interaction to get good electron hole capture in the LED. But then if we design the materials a little bit differently, we can get the electrons and holes to avoid one another, apparently. So this slide just sets out that if we put in a very simple criterion that the Coulomb interaction, remembering to put in the relative dielectric constant, is equal to KT, with a dielectric constant of 3, the capture or escape range is quite long. It's about 10 nanometers. That's the so-called Langevin capture range. So electrons and holes, if we inject them in an LED, are quite good at finding one another and forming excitons and emitting light. But how does the reverse process run, where we start with the electron and hole close to one another and we want them to move apart? And it's absolutely not trivial why that happens. And if it didn't happen, solar cells wouldn't work. So that the challenge is that if we've got an electron up on a high energy level on the donor, it can drop down to a lower level on the acceptor, and it might just trap there. And there are plenty of examples of where that happens and we don't have a good solar cell. But what we actually want is for the electron to travel far enough, fast enough, that it has overcome the Coulomb barrier and we've formed free carriers. I'll mention that it's something we've looked at a lot in Cambridge, and it turns out that, I mean, as must be the case, electrostatics tell us that as the electron and hole separate, there are quite strong electric field lines between them. Here we have the fullerene acceptor, here we have notionally some ordered regions of some polymer donor. But those electric field lines are there. They represent the fact that there's a Coulomb attraction that has to be overcome to separate the charges. And the local electric field turns out to be quite strong, and we can measure it. We can do some fast optical measurements where that electric field red shifts, stark effect shifts the absorption of the material in between. So if we look at the differential transmission, don't worry about the material system on the left, but if we look at the differential transmission, this is on a very, very short times. This is 10 to the minus 13 seconds, 10 to the minus 12, 10 to the minus 11, 10 to the minus 10, 10 to the minus 9 seconds. They're very, very short times. We have ultra-fast optical techniques to measure this. What we start with at very early times, these blue regions are bleaching of where there is ground state absorption. And then this red feature here is where we've got red-shifted, stark shifted ground state absorption, and that we can pinpoint as being due to this electric field. So we can actually track, and the key is that systems which work well manage to connect the early excited state to quite delocalized electron and hole orbitals, and the electrons and holes can travel quickly across many molecular units, and by the time they've slowed down, they're beyond their Coulomb range. That's the case for systems which work well. I'm just going to briefly mention something which is a current preoccupation, and that is that the story about triplets we tend to ignore for solar cells, but actually if a recombining electron hole, which must happen in a solar cell, end up in a triplet state, there is a risk that they can form, they can drop down to a lower lying spin triplet, exactly as they do in an LED. And I've taken you through the efforts that have been made with LEDs to make sure that triplets are not wasted. Now, there are ways of looking for triplets in organic solar cells, optical techniques which I'm not going to go through in detail. But we've been looking most recently, it's my postdoc Alex Gillett, has been looking at some of the more efficient non-fullerene acceptor solar cell systems. There's a famous one, Y6PM6, that was reported in 2019, and the efficiency has gone up since. And what we find in that system is what we call non-geminate triplet recombination, and that's this system here, PM6Y6, really is happening. It turns out that we have, I haven't put the numbers in, but it is quantitative electron hole capture ending up as a bound triplet back on the donor or the acceptor. So a whole load of different material systems we've looked at, and it's this non-geminate triplet which is something you cannot avoid non-geminate recombination attempts in a solar cell. It's there in the Shockley-Queisser paper. It's part of the thermodynamics. And what we find is that it's a very significant cause of non-ready recombination, and it accounts for a significant loss. Now, we actually have some designs, which I'm not going to tell you about at the moment, that engineer the triplet out of harm's way, and we have some exciting results where we think we can, if you like, do the same that has been done for organic LEDs, obviously in a different way for a different outcome, but do that triplet management, and that actually will raise the efficiency of organic solar cells. So I'm going to spend the last 5 minutes or so on something else, But the starting point is something I've told you about already, and that is that blue pixels in displays make use of this two triplets fusing to form a singlet process. So we have, we create triplets in LEDs because electrons and holes recombine statistically. Two triplets here have enough energy to form a singlet, and that's the story I told you earlier. Now, what happens if I rearrange the materials set? And you can almost always do that with molecular systems because there's so much scope to change the molecule, so that the triplet is down at half the energy of the singlet, which is the case for pentacene. So in that case, if I have two triplets, do they fuse to form a singlet, or do they not have enough energy? Or let me turn it the other way around. If I start with a singlet, might it undergo fission to form two triplets? Now, quantum mechanics doesn't mind which direction it runs in. So if you buy the story about fusion, where two triplets have more energy than the singlet, if two triplets have less energy than the singlet, we will get fission. So we split one excitation into two. And it happens. I should mention that we started this project in about 2008. It was the PhD work for Akshay Rao, who's now on the faculty in Cambridge, and Wilson, who's now in Toronto, Mark Wilson. And what this is a plot on a log time scale. So it's 10 to the minus 13 seconds at 100 femtoseconds to a microsecond at 10 to the minus 6. And what we can check from optical techniques is that we photoexcite the spin singlet state within 80 femtoseconds, less than 10 to the minus 13 seconds, it's split into two triplets, which are then long-lived. In this particular example, we split the triplets up into charges with the heterojunction with C60, and the time at which we see that is much, much longer, orders of magnitude longer. I show you that slide, there's lots of detail in it, but the key is that it allows, we know that this process is working. So why do we want to do that? Well, the problem with silicon solar cells is that they are limited because they are black and they need to be multicolor if they were to use the solar spectrum well. So silicon has a band gap of about 1100 nanometers. It's a 1.1 eV. So light at shorter wavelengths is absorbed. There are some infrared that just go straight through. But silicon treats any photon as though it were at 1.1 eV. And by the time we get to the visible spectrum, all the photons have got more than 2 electron volts, and all that excess energy, which is the gray shaded area, is dumped as heat. That's the principal loss that limits the efficiency of a single junction cell with the black body solar spectrum at 6,000 degrees to 33%. Now you can stack solar cells, and there's very interesting results putting lead halide perovskites on top of silicon. But another possibility that we haven't succeeded yet, we have many of the steps that look very promising, but another approach would be to have a top layer on a silicon solar panel. So we go from a solar panel to a red layer on top, which absorbs just the high energy visible photons and allows the infrared through. And the high energy visible photons are converted into 2 infrared photons. Now, if that could be made to work, then at a band gap, photons with twice the energy of the silicon band gap could be converted from 1 visible photon to 2 infrared, and we will double the current that we get from the yellow, green, blue part of the solar spectrum. And that, in principle, lifts the efficiency very considerably. It is actually making a tandem cell, but it's only 1 junction. So that's the big push. There are a number of architectures that may work. This one is due to Akshay Rao, and it's the one we're pushing pretty hard in Cambridge. So the idea is we have a silicon cell underneath, that the infrared goes straight through, and the silicon cell works as ordinarily, but visible photons are absorbed in our singlet fission organic, producing, so the one blue produces two infrared energy triplets, which won't emit, but we can transfer them into emissive quantum dots of lead sulfide, and they then produce infrared photons, which in principle we feed down to the silicon cell. Looks a bit complicated, but that's what we've been trying to do. And there's a paper which, if you look for it, you can find it on arXiv. It's currently submitted, where quite a lot of effort has been done to distribute lead sulfide quantum dots within a matrix of a tetracene-based organic system, where we have tetracene ligands and standard ligands for the quantum dots that have managed to allow us to get a well-spaced arrangement so that light absorbed anywhere in the tetracene matrix produces singlets that produce pairs of triplets, and all the triplets do find their way to the quantum dots. The problem at the moment is that the quantum dots are not emissive enough. Their luminescence yield isn't quite high enough yet, and that's where a lot of effort is going in. So if that were to work, then we might be able to have a cheap coating that would improve the efficiency of standard silicon solar cells. I should mention that if I've pitched this talk as solely driven towards applications, I'd be underselling what we do or what the field does, because there are huge opportunities to discover new science. And one of them that I'll just finish with is that it turns out it takes two molecules, here are two pentacenes nearby, to undergo this singlet to triplet fission process. And in some systems, there's an intermediate, which looks like two bound triplets. The two triplets turn out to have a binding energy, which is something people didn't know about, and they will later separate, and that's obviously what we want them to do. But whilst they're still bound, it turns out that the spin options, where we've got two spin 1 particles, do include making a spin 2 particle, making a spin quintet state. So we start off with our singlet. It undergoes fission to a sort of bound pair of triplets, which can rearrange to form an overall spin quintet state, and the electron spin resonance signatures of that quintet are now very well established in the literature. It's amazing what can be, how unexpected things drop out of this field. So on that final note, I will stop. That was my final slide, and I thank you for your attention. I'll be pleased to answer questions if that is possible.
Thank you very much, Professor Richard. This session was of about, I was expecting about 45 to 50 minutes, but it lasted around for 75 minutes. And the best part is that you have been able to answer, I think, most of the questions. And this is a wide spectrum of audience which are there, ranging from students of undergrad to postgrad to professors. So definitely the range of questions will be definitely vast. So on behalf of the National Academy of Sciences India Delhi chapter and the host institution, Deen Upadhyaya College, I would like to thank you from core of my heart, and to my fellow panelists, Dr. Poonam Kasturi, Professor Bhatnagar, who has been there in our department for more than 3 decades. And any concluding remarks from your side, then I'll close the session.
Well, let me first of all say thank you to you and your fellow organisers, and particularly to the patient audience who've stayed with me. And I'm sorry if I've taken more of your time than you anticipated. And it's a great privilege to be able to talk to you all. And thank you those who asked some posts of really good questions. I hope I managed to be illuminating on that.
Thank you.
Thank you all very much.
Thank you very much. Thank you. I have just seen that more than 300 attendees were there, and I'll be able to get the exact details later on after the talk itself. Thank you very much. Thank you very much, Professor Richard.
Thank you.
Thank you very much. All the audience. Okay. Bye-bye. Bye-bye.
Bye.